So today we're going to talk about the homework of chapter 7. Okay, so for first question, we want to look at the problem 7.6. So in here, we want to prove that the reflection coefficient is equals to this term and the transmission coefficient is equals to this term. So first, the relation between transmission electric field to the incident electric field is equals to this. And the relation between the reflected electric field and incident electric field is equals to this term. So extra, we know the B field and the relation between B field and E field is equals to this. So our incident power will equals to this term by the Poynting vector. And this term we know by the B is equals to this, so actually is mu B. Okay, can check. Actually is B over mu. Okay, so you can check that the incident power will equals to this, and the reflected power will equal to this. So the reflection coefficient is equal to observed value of incident power over reflected power over incident power. Okay, which is proportional to the electric field square. Okay, so we can easily prove that the reflection coefficient will equal to this term. And by similar way, we can also get the transmission incident power. Transmission power will is equals to this. So the transmission coefficient will also equals to instant transmission power of incident power. Okay, so become this term. And in here you will find that the square root of epsilon over epsilon 0 will equals to n. Okay, n. Okay, right here. Okay, so this will become n real of n. Okay, and then for the problem B, we want to evaluate this function. And so first we use the plane wave assumption. Okay, so E field is equals to this and B field equals to this. And so this the omega times E dot D conjugate minus B dot H conjugate over 2 will equals to this term. Okay, we just substitute the electric field and the B field we have into this equation, and by just numerical calculation, you can easily show that this term, okay, this formula can be solved as this. Okay, so as this term. So in here we know this term will become this term. Okay, and then we just take the epsilon 0 out. This first term, you will easy to find that this will equals square of reflection coefficient. Okay. Okay. So the second term will equals to observed value of in n square. Okay. So these two terms, if we separate the real part and imaginary part of n, you can easy to find that by numerical calculation. You can easy to find that this formula will equals to imaginary power of n times real power of n times omega times epsilon 0 times, okay, of this. Okay, so in here we can change we can change the formula of list to listen by this. N will equals to this C over V. Okay, so it's square root of mu epsilon over mu ring epsilon 0. Okay, so in here we can change N into this and get the results list. Okay, you can check by yourself. And then for the problem C, we want to look at the situation where for conductor. Okay, so for conductor D, we know that sigma will very bigger than epsilon 0 times omega. So in here, the reflection coefficient N can be reduced into this result. Okay, so in here for part A, we can easily show that the reflection coefficient is equal to this. Okay, as we get from part A, and then here we change N into this form, and then just separate the real part imaging part square. Okay, so oh, sorry, I missed a square list at this part, and we can easily to calculate this two term. Okay, like this, and then as we use the limitation, sigma is bigger, very bigger than epsilon 0 times omega. So we know that in this term, the C over omega times delta, this term will become very big. Okay, this term will become very, very big. So you will find that you only need to remain the largest order list, and also you only need to remain the second term of this and third term, and by numerical calculation you can get this, and also the transmission coefficient will become this under this approximation. Okay, and then for the part B, okay, as we divide this term will become this. Okay, as we divide in the part B, and then the same limitation of N equals to this. So we know that the imaginary part and the real part will both equal to C over omega times delta. So we have C over omega times delta square, okay, times of this. And here you can see that if we calculate the Ohm loss, we calculate the Ohm loss, we're 1/2 times E dot J conjugate will also give us this result. Okay, this two term will become the same. So in here we can know that the reflected, non-reflected part of transmission part, non-reflected part of the field will all consumed by the Ohm loss. Okay, so all the energy transmission will lose loss. Okay. And then for the problem 7.13, problem 7.13, in here we want to calculate the Fresnel equation. Okay, so 7.39, 7.41. Okay, we know that the reflection coefficient of E proton, reflection coefficient will become this if the electric field is perpendicular to the plane of incident, and the parallel electric field, if the E is parallel to the plane of incident, the reflection coefficient will become this. So in this problem, if we set n is equals to 1, and the media of sphere is n prime. Okay, so we will get these two. And here we want to calculate the angle, which is total reflection, which means the perpendicular part and parallel part will all will all have the reflection coefficient equals to 1. Okay, on these two, E2 equals to 1. So we can get two equations, okay, which is this get from perpendicular part, and this get from parallel part. And by calculating these two terms, we can get the results this. So if psi theta equals to n prime, then the reflection will occur. So the omega c will equals to oxide of n prime, okay, which is equals to this term. So we know that when theta is smaller than theta c, the reflection is partial, and when theta is bigger than theta c, and the omega is bigger than omega p, there will be a total reflection. And for part B is the practical problem of part A. Okay, so we just use the geometry relation, and we can get psi theta c have 2 equals to d over square root of 4 times h squared plus d squared. Okay, so you can by numerical calculation, we can get the result of omega p should equals to this term, and then we can substitute the h and the d provided by the problem. Okay, and we can calculate the result as omega p will equals to 4.6 times 10 to the 7 hertz. Okay, so okay, and then for the problem 7.14, we want to show the wave equation. Okay, very similar to the quiz 2. Okay, one of the quiz 2 problem. You can check by yourself. And so by the same approach, we just start from Maxwell equation with the source-free Maxwell equation. So in that, we can get this term. Okay, and by source-free, we know that the divergence of D will equals to 0, and D is equal to epsilon times E. Okay, so here, if we if we just consider gradient epsilon is not equals to 0. So divergent d equals 0 will give us this equation. So we know that the E will equals to this term. And also gradient of epsilon will equals to this. Okay, so the wave equation of this can be rewritten as this term, and we can substitute the divergent E we get from here into our wave equation. Okay, into our wave equation. So we get this formula. And here we assume we have two parts. Okay, we assume our propagation direction is pointing at positive x. So E field can be rewritten as these two. So we can take two parts to discuss. So for first part, we discuss the horizontal polarization, which is y component. Okay, so the EY will we substitute E with EY times plane wave. Okay, exponential ikz minus omega t. So we substitute into this equation, then we get the list. So in here, we know that list is the same as this. If we set q square is equals to epsilon times mu 0 times omega square minus k square. Okay, and f is equals to ey. Okay, so we successfully to show that for the horizon polarization, this equation will equals to our wave equation. Okay, and then for the vertical polarization, which is z component. Okay, so we just substitute the E field with EZ times also exponential ikx minus omega t. So in here, we can by numerical calculation, we can get these two, this term. And just also it will reduced as this formula. And then we know that we can check that this term or the partial z square of this can be rewritten as this term and can be summarized, okay, as this. And then you can see that this term is the same as the front part of this equation. In here, you can see d square dz square plus this second term, and the third term is equals to this, and the fourth term is this. So we can change of this in the equation by this. Okay. So we just substitute the result of this equation into our wave equation, then we can get this equals to 0. And here we can show that if we set square root of epsilon over epsilon 0 times EZ as F, big F, the 2 square of Z is equals to this. Then this equation also can fit the wave equation as F. Okay, just a lot of numerical calculations. So you can derive by yourself once, then you will know all the detail. And then for the problem being here, we want to use the WKB approximation, but this part is far beyond our class. Okay, WKB approximation, maybe you should learn from the quantum mechanical or quantum dynamic. Okay, so in here we will not explain the result, but we will show the answer we have to you. So if you have any interest about this WKB approximation problem, maybe you can check by yourself. Okay, so this is the first page of the WKB, and this is second page, and this is the third page, fourth page, and also the problem C also is related to the WKB. So this is the last page. Okay, so this is all of our today's course. Thank you.